Hi friends, welcome to follow up. Let's have a look at problem 269, Alien Dictionary. In this video, we are going to give a treatment for this problem by graph algorithm. So more specifically, we are going to use topological sort. So one algorithm for doing topological sort is the Kahn's algorithm. So let's first look at the problem statement. There is a new alien language that uses the English alphabet. However, the order among the letters is unknown to us. We are given a list of strings called words from the alien language dictionary, where the strings in the words are sorted lexicographically by the rules of this new language. So we are required to return a string of the unique letters in the new alien language sorted in lexicographically order, increasing order, by the new language rule. If there's no such solution, we are going to return an empty string. If there are multiple solutions, so we can return any of them. So here are three examples. So example 2 is very easy to understand because z comes before x, so we return zx. And example 3, actually here is a contradiction. So z comes from x, and then x comes before z, so this is a contradiction. So we return empty. So example 1 is sort of the generic case, but not that general. So we are going to look at two more examples in the analysis. The constraints are the following. First, the words has a length bounded above by 100. And each word in the list also has a length bounded above by 100. So the words I consist of only lowercase English letters. So with that said, basically we are ready to do the analysis. So here let's look at one more example. So in this example, like A, B, C and A, B, so this C comes before nothing. So this case, the required return is empty string. So for this example, so actually there are multiple valid returns. You can return ACZB or ACBZ. So in general, so if we compare two words, for example, the words in example 1, let's copy it here. So each pair of the words, like this one and this one, and this pair, right, or this pair, it gives us a order. For example, this one, so we first find the letters that are not the same. That is, WR are the same, so T and F are not the same. So T comes before F, right? So we can write like this. T comes before F, right? So similarly from WRFER. So we see that W is coming before E, right? And then if we examine this pair, so we see E is the same, so R comes before T, right? So now let's look at this one. So this gives us that, so if you look at the first letter, so E comes before R, right? And then if we examine this relations, so we see W comes before E, right? And then E before R, right? And R, then T, right? Then T, F. So we're going to have a return something like this. WER, TF. So we want to model this graph relation and then return this case. So this basically is the topological sort method. So here we are going to use the Kahn's algorithm to address this problem. So as a remark, so you can compare this problem with problem 207, so cost schedule. So problem 207 is actually a standard application of the Kahn's algorithm. In other words, one of the topological sort algorithm. So for this video here, we're going to write the code with some redundancy to make the idea easy, right? So first, I'm going to get all the unique letters. Get all the unique letters. So this actually is very easy. So let's call it a universe. So it's a set. And then we are going to iterate over the word for word in words, right? Then the universe will union all the words, so as a set. So word. So this set actually, because this is iterable, it will be the set of the letters. So we can actually print this universe just to have a feeling. And for example, this one, so the unique letters are B, A, C, Z involved, right? So this is the first step. So the second step is to model the graph structure. So this part actually is very important. So let's mark that. So we need to make the relations correct. So here, because we have get the universe, so let's do the graph like this. So we have atom, so we're going to use a set, right? So for atom in universe. So this is the node and their neighbors, basically, right? This is actually the adjacency list representation. So next, we want to use the in degree. So because we are going to use the Kahn's algorithm, we need to track the in degrees. So originally, all the nodes have in degree 0. So for item in universe. The reason we are going to first find all the unique letters because we don't want to miss some in the topological sort. So with this done, basically we set the graph, we set the in degree. So now we need to put the problem logic into consideration. So here, let me introduce a variable called m, that is the length of this list. So next, we are going to compare the pairs by sliding window. So for I in range, so start from 1, ending at n-1. And then the two lengths for the words get involved is nothing but length of words at I-1 and length of words at index I, right? And then we're going to start from the beginning, so to find or retrieve the first non-equal characters, so that actually produces a order relation. So then let's do this for G. Well, G is less than n1, just to pick one, right? So because this one is the previous one. So now what we want to do is, if G is less than the length of the second string or word, so let's track the letters. So words I-1, so at index G, and words I at index G, right? So if A and B are the same, we just need to continue. So let's say if A does not equal to B. So in this case, so we want to do a check if B not in graph A, right? So this we need this check. Actually, this corresponds to example 2 above, right? So which basically says that A comes before B. So you can see from here. So here C comes from B before B, and A comes before Z, and Z. So this let me check again. So C comes before B, right? CB and BC, right? So you can imagine. So this here AB corresponds to CB, right? So this relation gives us C comes before B. So this relation gives us again C comes from B because it's already checked. So we don't need to like here. So graph A at B, and we need to modify the in degree. So in degree of B is incremented by 1. So we need this check. The reason is that so if B is already in a graph A, so this does not make a difference. However, this part makes a difference. If we do not make this check, then the relation or the degree of counting is not correct. So with that done, so once we found a first non-same character, so we just need to break. So this is the one. So this is corresponding to this if. So otherwise, so we need to increment this g. So for the else block corresponding to g less than n2. So if g is greater than or equal to n2, actually it's equal to n2. So in this case, so this corresponds to example 1 above. So corresponding to this one, right? So after we check this character, so then it's already long equal to the length of this second one. In other words, the second one is a substring of the first one. So in this case, we just need to directly return empty string, right, according to the problem requirement. So this basically establishes the graph structure. So next, let's see. This is the for loop, right? So next, we are going to do topological sort. So here I'm going to use Kahn's algorithm. So for this, let me first get the queue. So collections. So I'm going to use a deck here. And then first I want to get those in the universe which has in degree 0. So here let's use a for loop just to understand this easily. Degree in degree items. So if degree equals 0, in other words, it's no dependency with other nodes. So we are going to append this character. Okay, right. So this way we have the beginning or initialization of the container or the queue, and then we are going to do the main step. So the traversal in Kahn's algorithm. So here basically it's breadth first based, because here I'm using as a queue behavior. So let's see, I'm going to use a visit as a set to avoid repetition and check in the invalid situation, or there's no valid topological sort. So then let's also get the topological ordering, right? So let's make it explicit. So now the standard traversal. Well, queue, so we are going to get a node. The node is queue pop left. Then what we are going to do is that we are going to topological ordering. I'm going to append this node to the list, and then we are going to add this node because it's already visited, and then we are going to check its neighbor. So for neighbor in graph a node, what we are going to do is that we check if neighbor not in visited. So let's see, then the in degree of the neighbor, it should be decremented by 1 because we have already added the node to the topological ordering. Because here the in degree decrement is corresponding to this one, right? Node to its neighbor. So what we are going to check is if in degree after this decrement is 0, we are going to append this neighbor to the queue. Let's see, neighbor. So basically after this, let's do a return. So here let's do return, or prepare the return. So we are going to return the string John, the same in topological sorting. So basically we need to check if this length of topological ordering, this is not topological order, let's take this, do a copy. If this length is equal to all the unique letters of the universe. Otherwise, so we return empty. So this is the problem logic. So here the way we wrote the solution is sort of verbose, but the overall purpose is to help better understand the procedure and the algorithm, so you can actually refine the code. Let's first do a check. Yeah, it passes one example. Now let's look at example 1. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So with that said, that's basically about it for this specific problem. So you are encouraged to modify the code to make it shorter or more organized, and also you can come up with some variants of the solution. So with that said, that's about it for this video. Thank you.